Welcome to the Science Café, hosted by the Weiss School of Natural Sciences at Rice University. In this informal session, Rice scholars will bring the excitement of scientific discovery to the general public. I'm Tom Killian, the Dean of Natural Sciences at Rice. In normal times, we would meet together in a real cafe and share food and drink as well as science. But I'm happy to have you here with us virtually, and we hope that we return to the in-person format soon. Today, we're going to learn about science for the quantum revolution. There's currently a worldwide effort to develop technologies based on the principles of quantum mechanics that are expected to revolutionize computation, communication, and sensing. The US Congress passed the National Quantum Initiative Act into law in 2018 to accelerate the development of quantum information science. Many countries in Europe and Asia also have national initiatives, and high-tech companies like IBM, Intel, Google, Microsoft, Amazon are competing in quantum technology development. So what is all this buzz about? How can the principles of quantum mechanics be used for such technological advances? What is a quantum computer? These are some of the topics that we'll learn about today. We are very fortunate to have two of Rice's own experts on quantum information science and technology to lead us through this discussion. Professor Kaden Hazzard and Guido Pagano, both of the Department of Physics and Astronomy at Rice. The format of the afternoon will be that Professors Hazzard and Pagano will present for about 20 minutes each. This will be followed by a question and answer session moderated by the Assistant Dean of the Weiss School, Lauren Capshaw. Attendees can submit questions through the question and answer function at the bottom of the screen at any time, and we'll answer those questions after the talks. So let me first introduce the speakers. Professor Kaden Hazzard is a world-recognized scholar on the theoretical description of quantum many-body systems. Systems such as clouds of atoms or electrons swimming in a lattice of ions in a solid. The building blocks of these systems appear simple, an electron or an atom, but the collection of these particles together display emergent collective behavior like magnetism or superconductivity that surprise and puzzle us and lead to technological applications. Professor Hazzard earned his PhD at Cornell University, did a postdoctoral fellowship at the University of Colorado at Boulder, and joined the faculty here at Rice in 2014. He's a leader in Rice's new initiative in quantum science. In his particular work, he develops new methods to harness the bizarre laws of quantum mechanics as a resource for precision measurements, secure communication, and advanced computation. Professor Guido Pagano is an experimental physicist who builds prototypes of a new type of computer, a quantum computer, that promises to outpace the fastest classical supercomputers. This technology may hold the key to solving intractable problems in code breaking, fluid dynamics, or drug design. He's also a key player in Rice's quantum initiative, and he specializes in quantum computers based on collections of trapped ions, trapped in electric fields and manipulated by laser beams. Professor Pagano earned his PhD at the Scuola Normale Superiore in Pisa and was a postdoctoral scholar at the Joint Quantum Institute at the University of Maryland before coming to Rice in 2019. So Professors Hazzard and Pagano will teach us the science behind the coming quantum revolution. And I believe Professor Hazzard will start first.
Can you see my screen? Everything's working okay? Somebody give me a thumbs up. Okay, good. So it's a pleasure to be here, even if here means, here in my house. But it's great to get the chance to interact with everybody who's here. And I'm going to tell you, like Tom said about this quantum revolution is what a lot of people call it, the second quantum revolution. I'll tell you a little bit about the first as well, and why are people excited about it. And the majority of my talk is actually going to be about, like, why are people excited about quantum at all? Because what Guido is going to tell you about is how we can build a quantum computer, how we can solve a lot of interesting quantum problems, but why would we even want to do this in the first place? So I'm going to try and motivate what this is all about and why it's challenging. And I would love to be there in person. Maybe as the pandemic winds down, I will let you buy me a beer. So if you want to chat more, feel free to send me an email and we can meet in the hopefully not too far future. So before I tell you about quantum, though, let me tell you a little bit about me. It's hard to say much after Tom's great introduction. I work a lot with quantum matter and with quantum technologies, in particular in this field of ultra cold atoms. So my friends cool atoms down to temperatures of 1 nanokelvin or thereabouts, which is 1 billion times colder than space. And once you get atoms really cold, you can do neat things with them that teach you about a lot of other systems, which are maybe not quite so fragile or exotic. And so I do not cool these systems myself. I am a theoretical physicist. And so I get to tell experimentalists what they should do and try to help them understand things, but without a lot of the dirty work. But let's see what's all this about. So we heard, there's this excitement about quantum. I think a lot of you are probably aware of this, but if not, starting in sort of 2017, things were blowing up. In The Economist, not usually where you read about physics, had a major issue about quantum technologies. Also the Financial Times, Wall Street Journal, definitely not your typical physics journals. New York Times had a couple years ago, or really a year and a half ago, a really nice article about some major milestones. So it's all over the place. It's hard to escape this. And it's come seemingly out of nowhere, this very esoteric sounding thing. And very recently, Guido's former boss has a startup company that has been the first startup to IPO in the quantum computing field. And it's over $1 billion stock that I think was the initial IPO. So this is not a small amount of money. This is $2 billion. Guido's saying, he's either saying peace or he's telling me it's actually $2 billion. And I think it's $2 billion. So it's a lot of money. You should be nice to Guido, I guess, or Guido's advisor, maybe. The point is, people are not only interested, they're willing to put their money where the mouth is. And of course, where there's money, you know what there's politics. And so the politicians have all started getting involved in this. And so there was this national quantum initiative of billions of dollars invested starting in the sort of impetus started in 2017. I think it was signed into law in 2019. Everyone from Ivanka Trump to Andrew Yang is tweeting about quantum. And I'm not sure I agree with everything in Andrew's tweet there, but it's okay. And if you haven't seen it, you should Google Justin Trudeau. He gave a visit to the Perimeter Institute for Quantum Physics, and he explains how quantum computing works to the media in attendance. And he does a passable job, so somebody prepped him good. Anyway, so if politicians and the media care about it, maybe we should at least figure out what this is all about. So other than my appeal to authority, why should we care about this? And I think that there are a few good reasons that I will try to get across to you. And this is really, in my mind, what the key part of the talk is. I want to tell you why we're so excited about quantum mechanics, both what makes it interesting and how we can use it. So one, it's really weird. I'm not going to get into all that weirdness, but I'll tell you a little bit of the weirdness and why it's so important. Guido is going to tell you more about the weirdness. Two, it's actually necessary to understand everything around us. And I think this may be surprising to you. Like, it's not at all apparent that, that I can look around this room and see things that really require quantum mechanics to explain. And I'll tell you about that. So, and then the third thing is that it has the potential to create these revolutionary technologies that Tom alluded to. Okay, so I'm going to structure the talk in the following way. Here's a baby. Okay, so what do I mean by this? So these are things you're supposed to care about. And I mean, look at this cartoon, right? Of course you care about it. He's adorable. So you care about this adorable baby. And so I'm going to tell you about why you should care about this baby, and other than the fact that I put a cute cartoon on there. And then I'm going to tell you actually about a threat to this baby and what's more threatening than a werewolf. So we're going to talk about the baby, then we're going to talk about the werewolf, okay? The werewolf is going to be what makes quantum mechanics hard. And then we'll come with a silver bullet and get rid of that challenge and explain how we're going to make progress on understanding these quantum systems, which will, Guido is the silver bullet. He will tell you more about this. So that's just to kind of latch yourself onto where we are in the talk. Of course, the fourth reason we care is that you can do 30% more washes if you use quantum. And you are starting to see that this word quantum has got such cachet that it's coming up in branding of all kinds of things. So ranging from, I think, dish detergent or something here to, of course, quantum healing flasks. And of course, this is all more or less BS, just brand, this doesn't have much to do with quantum, but it shows you how important people are starting to latch onto this word. So, okay, so let's get into the meat of what quantum mechanics is. I've kept saying quantum, but I haven't said anything about what is quantum mechanics. So quantum mechanics, when is it important? So it's important when you have things that are small. So this would be things like atoms or electrons, or when things get very cold. So this would be how cold you have to get depends on how small it is. But for things like atoms, it might be room temperature. It's not actually that cold. But for bigger things, you know, if I wanted to ask when would I start looking quantum, you might have to go to very, very, very cold temperatures, much colder than we can achieve in practice. And so this is tied to something that's very apparent, which is looking around, it's not obvious that quantum mechanics governs the day. So in quantum mechanics, you have these weird things called superpositions. Like you have a cat, you've probably heard of Schrodinger's cat. Schrodinger's cat is both dead and alive. Real cats are not both dead and alive. It's not even clear what that phrase means. And so that's just not something you see around you. And we'd like to understand why. What changes? Atoms are essentially both dead and alive. They can be in two states like that. Cats are not. Where does that change happen and how? And so a big goal is how can we understand that and how can we exploit that difference to do interesting things? And how can we bring that interesting quantum stuff to bigger and bigger and bigger scales? Okay, so the history of this subject is really interesting and not something we have time to get into, but to give you a sense, this all started to be understood from about 1900 to 1930. It's really like an ensemble cast. It wasn't somebody sitting alone and having a brilliant insight into how this all was going to work. There were really dozens of physicists, both experimental and theoretical, making real breakthroughs in how to understand matter and realizing there were contradictions with how we were understanding matter, and it didn't agree with experiment, and fixing all that up. And so this is where, if we're in person, I'd make somebody tell me if you recognize any of the physicists here. I'm guessing you can get at least one. But anyways, I think it's Einstein. Let me see. Do I have my pointer? Let me get my laser pointer. So on, you know where Einstein is. And then here, this is, I believe, Max Planck. And here is Niels Bohr, Paul Dirac, Werner Heisenberg, and Erwin Schrödinger. And so these are such famous physicists that if you're a physicist, you hear these names every day. You know, essentially day to day, these people were so foundational to everything that we know. They also ended up having an impact that went far beyond physics. And just like there are always good and bad aspects to scientific discoveries, this cast of characters is quite interesting, and I encourage you to learn more about, for example, Bohr and Heisenberg. Heisenberg was a Nazi and led the German atomic bomb program. So he has a great equation named after him. We're very thankful for that, but maybe not everything about his legacy is equally positive. And I think this is emblematic of scientific research in general. So there's a lot we can learn from that. What is quantum mechanics? So they discovered, I said, but what are they actually looking at? And so they were thinking about small things, atoms. And so I want you to think about something that's a little bit analogous to an atom, but we're not going to do quantum mechanics yet. We're going to start classically. When something's not quantum, we say it's classical. So basically, an atom is a positive charge with an electron or electrons going around it. And this is very, very similar to like the Earth with the moon going around it, or the Earth with a rocket going around it. And so think about this rocket. If I'm orbiting, like in this green orbit here, I'm at some radius orbiting the Earth. But I can fire my rocket engine. And if I fire my rocket engine, I can change the radius. I can go out to this kind of red orbit. Right, so I just put on a little burst on the rocket. Now I'm going in some new radius. And I can pick whatever new radius I want. If I want a big radius, I can do that. If I want a little radius, I can do that. And I can pick whatever. In quantum mechanics, this is no longer true. In quantum mechanics, only certain special radii are allowed. And if this diagram is too much, you don't have to understand anything about this diagram, except to know that there are very special radii that are allowed. Okay, so 1, 2, 3, 4, they're discrete. They come in units. That's where the word quantum comes from. It's a quantum change, meaning it's a discrete change, not a continuous change. Okay. And so this idea ends up having very profound consequences for everything. And a cartoon to keep in mind about why this is working is that you can think about waves, just like water waves, kind of living on these orbits. And these water waves have some length that they like to wiggle at. And the orbits correspond to when you have a certain number of wiggles as you go around the circle. Okay. Again, if that doesn't make sense, that's fine. Just ignore it, but there are certain discrete orbits. That's what you want to take home from this. But I am going to try and connect to this picture later, which is why I'm introducing it here. So this predicts discrete spectra. If you have these discrete levels, these discrete orbits, then when the system emits light, it can only do so in discrete ways. It has to emit light to get me from one orbit to another orbit. And that only comes in certain colors. That corresponds to those different types of emitting light have different colors. And so I just think this is a beautiful picture of all that. And it was looking at spectra like this. This is the whole periodic table, or most of the periodic table showing these different spectra. And it was looking at spectra like this that were a major motivation for the people that invented quantum mechanics to do so. Okay. So now what I want to convince you about is that this quantum mechanics that was developed is actually really important, not just for atomic spectra, but for all kinds of things. So the air I am breathing right now is made of oxygen molecules. Oxygen molecules are basically two atoms, and these atoms can vibrate back and forth, or they can rotate. And consequently, the atoms can carry energy, right? So if they're vibrating, they're carrying some energy. If they're rotating, they're carrying some energy. And if you just went and ignored quantum mechanics and asked how much energy would they carry, it turns out they would carry a certain number that we know how to go calculate. And people did this. But when you go measure how much energy they're carrying, calorimetry or something like this, you can see that your answer is totally wrong if you treat it as a classical system without quantum mechanics. In fact, quantum mechanics changes the answers totally. It changes not just the numbers, but how it depends on temperature and pressure and everything. So this is very important to understand how air works. And I can't think of much that's more ubiquitous than that. Or the laptop that you're staring at, or the tablet or phone or whatever it is. This has probably got a bunch of metal on it. The metal on this has electrons. You should think about it as electrons floating around inside the material. Here's an image of those electrons. And in silicon in particular, nickel silicon mixture, and they are not little points, but they're sort of spread out, just like they're in orbits, but not circular orbits. They're orbiting over the whole material in some random pattern. Okay, and that even understand something simple, like is a solid metal like aluminum or an insulator like silicon, you need quantum mechanics. You can't answer that question without it. So that's a very everyday sort of aspect of quantum mechanics, but it goes beyond the everyday. There's not so everyday applications, like this MRI machine. At least I hope you're not an MRI machine every day, but maybe more positive things like this bullet train that's levitated by superconducting magnets. It could be levitated by superconducting magnets. And it turns out that superconductors are intrinsically quantum mechanical. And we can understand this going back to this atom picture. So what's going on in a superconductor is, again, the electrons can orbit. But remember we said that you can't fire your rocket engine and make a small change? That's really the same thing that's going on in a superconductor. So the reason metals are not superconductors, they don't conduct perfectly, is because there's always dirt in your metal. And so your electrons bounce off the dirt. Okay, and the reason is even if I add just a little bit of dirt, the electron can just bounce a little bit. But if your electrons start behaving more quantum mechanically, like they do in a superconductor, now they can't just bounce a little bit. They come in discrete orbits. And so you actually, a little bit of disorder won't cause you to scatter off. And so you will just conduct perfectly. The electron will keep going. Or thinking of an atomic analogy, this little picture I'm showing on the bottom left, this is a circuit made of a superconductor. You should think of this as a ring, and the electrons are going around in orbits around this ring, just like electrons in an atom do. And just like in the atom, they have to fit some number of wavelengths as they go around this circle. And that's this sort of quantization. That's this discreteness that makes them robust to the disorder. This device, for what it's worth, has an appealing name. It's called a superconducting quantum interference device, or SQUID. And so it's a superconducting squid. Okay, cool. So, and then it gets even more fun because we can do things like levitate a frog. So let me see if I can play this video. If I can't, that's okay too. You can Google levitating frog yourself. Oops, there we go. So don't ask me why you would levitate a frog, but people can do this using superconductors. So that's a not so useful application. I don't know, an application of some type. So, and then there's the truly bizarre. Let me just say this real quickly. This will probably make no sense, but maybe it'll make enough sense to give you a sense it's truly bizarre. So imagine that I have a very ordinary looking material like this. It's gallium arsenide. This is what's known as the 2D electron gas. People do experiments on this where they put them in magnets that don't look so different from this horseshoe magnet. And they run some voltages and currents. And from these voltages and currents, physicists know how to tell what the charge of the current carriers is. So if you have a bunch of electrons moving around, you do this experiment and you can figure out what the charge of the current carriers is. So people did this experiment on gallium arsenide, and quite shockingly, the charge carriers had a third of an electron charge. And let me be clear, the smallest charge we know of in these systems is the electron charge. Yet they're behaving exactly as if they have a third of an electron charge. And in fact, not just roughly a third, but like to 10 decimal places or 8 decimal places, it's a third of an electron charge. So that's very strange. And what's happening is there are collective motions of all the particles that move together. And the fact it's at almost exactly 1/3 is again an aspect of this quantum rigidity that comes from the quantization of energy levels. This continues to be a really motivating topic of research. This was found in the 1980s, but is only beginning, so certain aspects of it are understood, but it still motivates a lot of research about exactly what's going on here. So all of this is just a way to say that when you have lots of particles, especially quantum particles, they behave different. And individual gold atoms does not look like a bunch of gold atoms put together, and it can be very difficult to predict what the whole system does. And that gets us to what I'm trying to say here. Quantum is hard to understand. Many bodies is hard to understand. Many particles are hard to understand. Putting them together makes it really hard to understand. So our baby has its thread, as the werewolf. This isn't a particularly menacing werewolf, but there we go. So, so one way to know that it's hard to understand is because you've been listening to me for 10 minutes now, and I'm hard to understand. No, so but if you want a more technical reason, here's a system that has 50 particles. Let's pretend we can simulate that system in a supercomputer. We actually can't, but let's just pretend. And now let's imagine that I'm going to add just one more particle, barely changing the system at all. Well, now that particle has multiple states it can be in. Maybe it sits over here, or maybe, I can rotate it in one way or another. So let's say it just has 2 states. The issue is this actually doubles the total number of states in my system, because I could have any state I had before, but now I have to multiply by 2 for the 2 states of the new particle. So to simulate just 51 particles, I need 2 supercomputers. And to simulate 52 particles, I need 4 supercomputers, and so on until I need a lot of supercomputers. So I think 56 is I don't know, whatever, 64 supercomputers here. And as soon as you try to simulate just 100 particles here, you'd need something like as many supercomputers as there are atoms in the universe. So you would be very much in trouble if you tried to simulate things this way. And this turns out there are tricks that let you get around this issue for classical systems, but not for quantum systems. And that's what makes it hard. Okay, so how are we going to solve this problem? Sorry, before I say how I solve, this is just another example. This is some data a student of mine, Eduardo Ibarra Garcia, had calculated compared with some experiments. These experiments are actually the coldest Fermi systems in the world, and the calculations for like one data point are thousands of computer hours, and that's for 8 particles. So if real matter is made of a million particles, solving 8's pretty far away from that. So we're proud of it. It took a lot of effort, a lot of smartness on Eduardo's part, but still, long way to go. So the way we're going to solve all this, here's our silver bullet, is we're going to use a dream of Feynman's. That's the crazy uncle up at the top that I think Guido is going to say a little bit more about, which is to mimic the quantum system that we care about. I showed you this picture of a metal earlier, with some new quantum system that Guido is going to engineer in his lab, or someone's going to engineer in his lab. And so you're building an experiment that's more tunable, that's cleaner, that's more probable, lets you change variables you couldn't change in the real system, and you can study it in that new setting. And so now you can add particles and it doesn't grow in this huge, awful exponential way, and you can still simulate it, unlike with the supercomputers. And the real labs don't look quite as simple as that cartoon. They look more like this, but there's still some reasonable experiments that you can do at a university or a company. And so that's really the answer. And as you add more and more flexibility to these quantum systems, you can essentially not just make things that look like ordinary lattices. So lattice in a aluminum is just kind of a square. The atoms sit in a square, the electrons move in a square. Here, the particles that are the analogs of the electrons can live in very complicated, interesting geometries, like an Eiffel Tower. This is from a group in France that each of those dots you're seeing is an atom. He is trapped in space. And we can actually start programming these systems. So not just tuning, say, the lattice spacing or something like this, but manipulating where we put the atoms and move them around in time and turn interactions on and off. And so this is very much like a computer. You can feed it a set of instructions and it will output answers. And these will let you solve those problems about materials, about fractional quantum Hall effect, about interesting things like that, that we can't solve on supercomputers. And in my mind, that is the killer app that we know of for quantum computing, to simulate materials, catalysis, enzyme binding. And amazingly, and I'm not going to talk about it all, is that this has other applications beyond physics. You can factor numbers faster than a classical computer can by using these systems. You can search databases, and people fantasize that you can do optimization and machine learning and getting more speculative things. So just to summarize, quantum is everywhere. We have to understand it if we want to make progress on understanding materials and chemistry and things we care about. And there's all kinds of fascinating stuff that has many open questions about it that we don't know how to understand. It's also a new resource that lets us build new types of computers and also sensors and communication devices I didn't talk about that will let us answer some of these questions. And there's a whole emerging new field that's pushing quantum at this complexity frontier that is ongoing. And at Rice and elsewhere, we are asking, what capabilities will these engineered systems provide us, and how can we actually build these things, which Guido will tell us more about. So that's it for me, and thanks for listening.
All right, thank you. All right, so I'll take it from where Kaden left, and I will talk more about the second quantum revolution from a more applied and experimentalist perspective. So how can we actually harness this quantum revolution to build devices and to basically address all the problems that Kaden talked about? And I want to point out that we talk about second quantum revolution because the main, so there was already a first quantum revolution, which Kaden talked about, which led to many devices that we use in our everyday lives, from our iPhone or from lasers, from anything that involves a solid state device. It actually is built on the understanding that we gained from the first quantum revolution. The second quantum revolution relies on a key aspect, that we can manipulate and detect individual particles. Like, for example, here in this picture, you can see that each bright dot in this picture is an individual atom that we can resolve and we can manipulate. We can encode information in it, and we can also solve problems eventually. So let me take an historical perspective, and as Kaden mentioned, Feynman is really one of the fathers of this quantum computing aspects. So if we have control on a quantum system at such a great level, so that we can control the individual components, we can actually simulate nature, because nature isn't classical, it's quantum at its very core. And so if we want to build a computer or a simulator of nature, we have to have it quantum mechanical. And if we don't, if we just use classical computer, and I will talk about that, then we have this exponential problem, exponential scaling problem that prevents us to gain some real understanding. So this idea took off after the 80s when Feynman launches. And so Peter Shor was the first one that found out theoretically that if you had a quantum computer, you could actually solve a very, very practical problem, which is prime number factoring. So if you had a quantum computer, you can factorize big prime number, and you might say, why do I care? Well, actually, it turns out that all our cryptography protocols, all our credit cards, and all our financial transactions are based on the fact that it's very hard, it's exponentially hard for existing classical algorithm today to factor a very big number in prime factors. And so if you had a quantum computer, you can actually crack pretty much everything. So of course, this spurred out, basically launched a lot of excitement about these quantum devices. However, quantum mechanics, as you might have understood from the previous talk, is analog. So our computation, and I will talk about it in a few moments. Right now, the classical computers are classical. So you either have a 0 or you have a 1. So it's inherently robust to errors. You can manage errors in a fairly easy and intuitive way. However, quantum mechanics is really continuous. You don't have only 0 and 1s. You can really go beyond 0 and 1s, and you can have any superposition between the two. So you need to correct for errors. But actually, theoretically, this is possible. This has been proven to be possible. So the take-home message is right now there is really no fundamental laws of physics that prevent us to build a quantum computer. So to actually have a quantum system that we control so well that we can use to process information and to solve interesting problems. However, we are in 2021 now, after several decades, and we don't have a quantum computer yet. So where is the matter? So let me take an historical perspective and take a step back and tell you a little bit about how a classical computer works. So a classical computer is also based on quantum mechanics and is based on a transistor. So here you can see the first transistor in 1947. A transistor is basically an electrical switch. It's something that we can control its state of, and the bit of information is physical, is encoded in a 0 or 1, either the switch is off or on. Okay, and this is of course done manipulating electrons. So there is an empirical law which is called Moore's law that says that the number of transistors on microchips doubles every 2 years. So basically this means that right now in 2020, our laptop have 50 billions of transistors. So that tells you, that there was a huge effort to integrate the system and to increase the computing power. However, by making this object that was first invented in 47 smaller and smaller and integrated, but right now we are really at the boundary of what we can do, because if we make it smaller, then we are basically hindered by quantum effects. So quantum really plays a role, and it's basically threatening this Moore's law. Okay. So this is the reason why, Kaden mentioned this. There are many companies, he mentioned just a few, but actually there are many that are betting on different technologies. Indeed, in the right now, we're if we compare the classical computer trajectory and the quantum computer, we're probably even before the transistor, because there it was, at some point, it became pretty obvious that the transistor was the right technology to bet on. And there was a huge effort of the whole world to go after that technology. So now here, there are many quantum systems that fulfill the requirements to build a quantum computer, so that you can basically manipulate individual quantum objects. And this can be atoms, or this can be quantum dots or superconducting circuits. Each one of these logos here corresponds to a company. You might recognize some of them. Google and IBM, for example, are investing in superconducting qubits. There are other startups that are, using trapped ions. There are other companies that are using photons, etc. So I want to tell you a little bit about one approach, which involves atoms. And there is also another quote of Feynman that is very interesting. He says in '86, he said that basically it's ridiculous to consider to write a bit of information of a single atom instead of 10 to the 11, which is what we do in a classical computer. However, he says that this nonsense is really entertaining. And I hope you also find it entertaining, but I want to point out that right now is not only a professor kind of a divertissement, but it's actually something that people are really going after with real money, as Kaden pointed out. So let me tell you a little bit about how a quantum mechanics work. I'll give you a crash course in quantum mechanics, and I'll tell you just the two basic rules of quantum mechanics. So as Kaden mentioned, there are discrete levels in quantum mechanics. So quantum objects are waves, and waves can be in a superposition state. So if you have two states, you cannot be only in 0 or 1, but you can be in a superposition. Okay. And the second rule, so it's in a certain sense is weird, but it's very straightforward in a certain sense. However, the weirdness of quantum mechanics comes with the second rule. So that says that rule 1 holds as long as you don't look. Okay, so this means that if we have this fancy superposition and we look at the system, unfortunately, we have a probabilistic outcome. So either we will get a certain p with a certain probability p, we'll get 0, or we will get 1 with 1 minus p if we have a quantum system with just 2 levels. Okay, so you might say, wait a second, how do you want to build a computer with something that is inherently probabilistic? Well, I'll tell you a little bit about this. So in the following, I will use 0 and 1 or up and down, but it's just 2 degrees of freedom, you know, two levels, and where we encode information. So that's all we need to build a quantum computer. And I want to basically let you see an experiment that we can run routinely now in our labs, where we have an atom and we shine a laser onto this atom to manipulate the state, to basically control the probability of observing 0 or observing 1. And so you can see in this case quantum mechanics at work. So let's say that we take a single atom and we shine a laser onto it, so that basically we know that what's going to happen is going to change the state of the atom. So we're basically changing the orbit in a certain sense, like Kaden was saying. So we're manipulating a single quantum object. So what do we see if we do this experiment? Well, these are the real data. These are the raw data that we see. Of course, as I told you before, as soon as we look, we get a classical outcome. So either we get 0 or we get 1. Okay. So, and you might say, okay, this is just like, you know, flipping a coin. Like, for example, here we get most of the time 0. Here, sometimes it's just probabilistic. We go up and down and we get 1/2 of the time 1 and 1/2 of the time 0. Here we get mostly 1. So, but I mean, if you take the average of all these measurements, actually you realize that this is not simply flipping a coin. There is probability encoding in nature, but this probability evolves deterministically. So we can actually control how this probability evolves deterministically by basically controlling it with our laser. And you can basically think about it this way. You have a box, and as soon as you open this box, which means when we actually look at the system, we project it and we either get 0 or 1. But if we keep the box closed and we don't look at it, but we just turn the box in a deterministic way, then we can actually have a quantum system that evolves in time and that basically behaves according to the rule of quantum mechanics, and we preserve this fragile quantum superposition. And I'll give you a nice visual explanation of quantum mechanics. So look at this cube. You can actually, your brain can project it either in one way, say this one, or the other way, say this one here. Oops, sorry, yeah, this one here. So, so this means that as soon as you project it, you will see it either in one way or the other, but there is really no way for you to figure out, you know, to see it in both ways. But when we are here, we're actually exactly in a superposition of both of them. But as soon as we look, we project it in one way or the other. And so this visual analogy will be very useful to understand now how we explain another feature of quantum mechanics, which is entanglement. So, so quantum mechanics, quantum computer in general, are based on two features. One is quantum superposition, which we just covered, and the other one is entanglement. Entanglement means that there are some very basic and intrinsic correlation that can be created in a quantum system. Like, for example, say that we, instead of having just one atom or one bit of information, we have two, okay? In principle, we can create such a superposition of two states. And this is very special because as soon as we measure one qubit, the other one will be automatically projected in a correlated state. And you can see it again with this visual interpretation. So if you have two atoms that are far apart, or two cubes in this case, you can see, if you focus on one cube, you can actually see, you know, both states. You can project it in both states. However, if you bring them close together, either you see them both in one way or you see them both in the other way. And that's exactly the principle of quantum correlation in a certain sense, explained visually. So that's exactly the power that lies in quantum computers. So basically, this type of correlation allows you to tackle problem in a more parallel way, because you can input many states at the same time and then get an answer faster than you would do with a classical computer. So I would like to tell you a little bit. This is going to be maybe a little technical, but I think it's fun to really see how how these devices can be built from the ground up. So what we do when we want to build a trapped-ion quantum computer, we have to confine this particle. We want them there. They are our quantum register. And so because of Maxwell equation and Gauss law, we cannot use static fields. So the way we do it, we apply a varying voltage that oscillate in time. And you can see that basically a video is worth 1,000 words. So this is exactly what's happening in real time. So if you play this video, you can think that this is the charged particle, and this saddle point potential that is spinning around is the voltage, is the electrical potential that we're creating. And in this way, we can actually confine in 3D these charged particles, so we can see them. So here you can see each dot is well resolved, and each bright dot here is a single atom where we can encode information and process it. So here is a video of how we actually assemble the quantum hardware. You can see live the atoms that are popping up because we shine laser onto it, and we can collect fluorescence. So we actually know where the atoms are. We can move them around. We can write on them information, and we can also use the fact that they arrange in a crystal and they talk to each other. So this is the principle that I was trying to explain before. So we had two atoms. If they are close together, either we can, if we entangle them, either we we see it in all down or we see in all up. So we can actually entangle them because they interact, because they're charged, so they repel each other. So they have specific ways of motion, and we can actually use this to create entanglement and to harness quantum information. And I'll give you a very basic idea of how we can create entanglement in the system, which is the basic logic operation to build a quantum computer. So say that we want to create an entangled state between this atom here and this atom here. So the way we do it, we apply a spin-dependent force. So here we basically want a truth table. We want to have, if the atoms are in the same state, they basically will move in the same direction because we're basically pushing them with a laser in the same direction. And the push really depends on the state. That's how we actually process information. If they are in different state, they will move in different direction. And this truth table basically allows you to build a state like this. If you time it right, you will actually create an entangled state. Don't mind the equations, but the point is that by manipulating atoms and lasers, atoms with lasers, we can create all the building blocks to build a quantum computer. Now, I'll stop with the technical stuff and talk a little bit about the perspective. So you might think I'm crazy because I'm saying that we're going to build a computer out of atoms and lasers. So people might say, well, how are you going to scale it up? It's very hard to really integrate these systems. Well, people are thinking about this, and there are several approaches. These are still, these are fairly recent papers that basically outline a possible strategy to basically build this scalable quantum computers. One way is to have multiple modules of trapped ions that are basically interfaced through photons. So we can extract information from the photons that these atoms emit, and we can basically make these photons interfere, and so we can create entanglement among remote modules. So this is something that all the building blocks have been basically demonstrated. That's why people are now investing a lot of money to really scale this up. Another approach is maybe more intuitive. You just have a very large ion trap where you have multiple zones, so you can accumulate many qubits, and then whenever you want to move information around, you really move physically the ions from one side to the other, and you process information in this way. So probably, at the very end of this journey, I anticipate that these two approaches will probably merge together. So and in the very same way that people built, complicated integrated circuits to run classical computers, in the same way, in our field, we're trying to basically make the system more compact and put all the stuff that is right now in the lab. You saw the picture of shown by Kaden of a very messy lab with large optical tables with a lot of optical components. So the challenge now is to really bring everything together and to integrate everything in a single chip in the same way that has been done for integrated silicon wafers. So with this, let me take a step back and say, do you think I am crazy that I'm proposing to build a quantum computer out of atoms? Well, if you think about the ancestor of the computer today, it was actually this arithmometer, which was built by Blaise Pascal in 1642, and it was just a mechanical device that with wheels that allowed you to do basic arithmetic operations like sum, summation, subtraction, etc. So this evolved to the transistor, and now the computer looks like this. So as you see here, really there can be dramatic shift of paradigms from one model of computation to the next. And maybe it's not inconceivable to think about something that is right now unknown, or it's very hard to imagine, but there will be the quantum computer of the future, and maybe it will be based on this technology, maybe it will be based on another technology like superconducting qubits or neutral atoms or photons. And let me finish saying that there are multiple uses to this quantum computer from the fundamental perspective. So, and this is where my interests lie. So I think once we build a quantum device that can go beyond what classical devices can do right now, we can solve multiple problems at the fundamental level. So, for example, we can talk about high energy, or we can solve how complex molecules bind together and solve, for example, for their energy states. We can basically tackle complicated materials like superconductor that we saw in the previous talk. So there is really plenty of room on the fundamental side, and on the applied side, there are multiple things that can be addressed now, and well, that are hopefully we can address in the near future. Like, for example, we can think about that, once we know how to solve a molecular system, we can actually think about ways to find new pharmaceuticals, or we can, once we really understand materials, we can find ways to create new materials, so we can tackle classical optimization problem. Of course, there is cryptography. There is also very big applications, because as I told you, once you have a quantum computer, you can factorize prime number. So with this, let me thank you for, let me thank you for the attendance, and I'm looking forward for any questions you might have. Stop sharing.
All right, thank you to both Professor Hazzard and Professor Pagano. And to everyone who's listening now, please feel free to submit questions through the Q&A function as we're talking here. We've got a few to get us started, but I'm sure both of our speakers would love to answer as many questions as possible. So Guido, you talked a little bit about cryptography and encryption a couple of times in your presentation, but could you talk a little bit more about what's going to happen to our current encryption techniques? Are there going to have to be new techniques that are developed once we have quantum computers online? And then also, how do you encrypt data on a quantum computer?
Yeah, that's a very good question. So definitely there is a whole, a whole field of quantum cryptography that studies exactly this problem. So basically, once you have a quantum computer, how you devise, how do you devise a system that is unhackable? And actually, it turns out that there are ways to do that. For example, one way is to use still quantum mechanics to avoid this, and to use entanglement, because for example, in a communication channel, if you send an entangled state and there is somebody that is observing some of the particles, you will figure out right away on one of the two ends. So there is a whole field that studies exactly this problem, basically how to use entanglement to create a secure protocol of communication. And so, yeah, and for the memory part, that's a very good question. And I would say right now there is probably, so how you encode data, that's the question. And so that's a very good question, because once you basically, once you have a complex quantum state, one of the problem is exactly to store that state on a classical device, right? Because then you have to really use a lot of memory. And so right now, I think one of the best approaches would be to basically have a quantum computer where there are some qubits that are very robust and that can store quantum superposition for a very long time. And this is already happening right now. For example, for trapped ions or isolated atoms, the coherence time, so the time that you can store a quantum state, has been estimated of the order of 10 minutes, which might not be, you know, this is without any correction. So you might routinely, like, you know, do operations to correct these states and use quantum error correction to avoid the state to decohere. So I think a combination of using very robust qubits that already exist now, and also using quantum error correction might, you know, lead to basically, you know, data encoding and storage, quantum data encoding and storage. But most of the effort right now is to mainly on the processing of the of this quantum circuit.
Thank you. Okay, we have another question that's asking about time crystals and if they're at all used in quantum computers. So does one of you want to maybe just introduce the idea of what a time crystal is, and before you answer whether or not there's a role for those potentially in quantum computing systems?
Yeah, so it's funny because I actually did 2 papers on time crystals, and so time crystals are I wouldn't say that they are directly connected to quantum computers, because time crystal is just a new state of matters, and there are a lot of caveats, you know, around there, because, you know, a time crystal is basically something that oscillates in time periodically. And you might say that even fireflies that synchronize themselves, right, and they fire all at the same time, might be a time crystal, right, because they, you know, they self-synchronize. So what is a time crystal? So this is a long discussion that people are having, and you know, there's still ongoing, there is a still ongoing discussion. But basically, a time crystal is something that is based on quantum effects, a quantum many-body effect, that stabilize this oscillation. So unless, because otherwise you can find many examples of something that oscillates over time that there is not a time crystal according to this definition. So given this definition, there is a link between time crystal and quantum system, but it's not, and quantum computers, but it's not a direct link. It's not something that you say, oh, once we have the time crystal, then we're done. So the time crystal might be useful maybe more for quantum metrology, because you have a very precise oscillator, and maybe you can use that to basically to build some quantum technology. But for quantum computer, I'm not sure.
Thank you. So Kaden, I think this question is a good one for you. Someone's asking, you had mentioned, you know, these headlines that are coming out where people are claiming quantum supremacy, Google, and possibly some groups in China. So how big are these milestones? Can you put these into context? How do we know, like, what's the hype and what's like real behind these announcements?
Yeah, I mean, so this is not only a great question for the talk. I mean, this is a question that the whole community is grappling with, exactly what it means. So, so let me just rephrase this and also give a little bit of the background for people who are not as familiar with it. So, so there's this idea of quantum supremacy or quantum advantage. These terms sometimes mean different things, sometimes the same thing. I'll use them interchangeably. And the idea is this is a milestone where you can be really sure that whatever your quantum computer is doing, whatever this device that you've built is doing, it's doing something that a classical computer could not do nearly as efficiently, right? And that if you made these systems bigger, that the quantum computer would get much more efficient relative to the classical computer. And so there have been at least 2 claims to have demonstrated this, one coming from the Google group in 2019, and one coming, I think this just in the last few months, from John Wei Pan's group in China. And using very, very different sorts of technologies. One is the superconducting qubits we heard about, and then another is using essentially light, photons of light. And what I think everyone will certainly concede is that whatever they were trying to accomplish here, the claim is not that it's useful. So this is really important. So the claim is not that we have to do some algorithm or solve some problem that people want to solve because it will let you make better drugs. To show this supremacy, all you have to do is show that it's better than a classical computer at something, right? And so people have designed some things that are as advantageous as possible for the quantum computer and as disadvantageous for the classical computer. So put utility out of your mind. The question is just, have we even showed that a physical system exists that's not a classical computer? That's what the question we're really trying to answer. And now the question is, have they showed that? So is the quantum, how supreme is the quantum supremacy? And this is where it gets a little tricky. So if you look at the Google experiments, I think it ran in something like 3 minutes. And I think the fastest equivalent calculation we know how to do on the largest supercomputer in the world, initially it was something like 300 years, I don't remember the exact number, but now the claims are that nobody's actually done it, but that it could be done in 3 days. Now this is still a pretty big advantage, right? But it's not as impressive as before. And so then the question is, maybe there's a better trick that nobody's discovered that could bring the classical computer closer and closer and closer. And so really proving beyond a doubt that there's no way to make that classical system faster is the hard part. But so the way I would phrase it is that right now we have a maybe factor of 10,000 faster quantum computer than a classical computer for some special task. And that there's significant evidence that as you make the quantum computer bigger, the advantage it gets over the classical one gets bigger and bigger and bigger, right? Which is exactly what makes these so powerful. It's this exponential scaling of the number of supercomputers that I showed. And so that seems pretty clear, but of course, you know, if a skeptic has a doubt for the current quantum computers, we'll scale them a little bit bigger, and hopefully it's easier to add 1 or 2 or 3 qubits than it is to, you know, to scale the classical algorithm. And we'll almost certainly find out very soon. And I expect the ratio of the quantum to classical advantage to grow enormously. Now, there's some technical details about the China experiment that I won't get into. In many ways, so it's an extremely impressive experiment. It has some drawbacks and also some advantages compared to the Google one, and I'd be happy to talk more, but there are lots of questions, so we should maybe move on to those.
Yeah, there's actually a follow-up question. So, you know, is it always going to be that these quantum computers are kind of built for a specific purpose to achieve these milestones, at least for the time being?
Yeah, that's so no, if that was the case, so maybe for the time being, but if that was the case, these would not be very useful or very interesting problems. So the key point is the very last slide up to the summary that I showed, which is the programmability. That is the same tools you need, the same sort of inputs and same sort of steps you need to run that supremacy experiment are identical what you would need to do useful experiments. You know, run useful algorithms. And so you could ask, so why didn't somebody run a useful algorithm? Why did they do this kind of, somebody said, so it's basically a game. And the supremacy absolutely is a game. It's sort of a race between the quantum and the classical hardware. And so, but that doesn't mean that all of quantum computing is a game. The reason they didn't start with the useful stuff is because it's actually mathematically harder to prove stuff about classical algorithms for the useful stuff. So if you want to simulate a molecule, okay, thousands of physicists have tried to do this, and chemists and engineers have tried to do this for decades, and we still suck at it. And so there's been a lot of money poured into it. We still aren't very good at it, but we don't have like a rigorous mathematical proof in the way that we do for a supremacy experiment that it would be hard on a classical computer. And so really the only reason they do these very funny looking experiments is because it makes it easier to prove that the classical system is as close to good as you can get. It's not that the quantum computer is, as far as we can tell, actually better at solving those sorts of problems. But these devices at Google are fully programmable, and other companies are fully programmable and can run any quantum circuit, any quantum algorithm that you would like to.
So we're right at 5 o'clock, but if you two are willing to hang out for just a couple more minutes to answer a couple more questions, I would like to do that. Thank you. All right, so we have a question here that's asking, given the inherent sensitivity of quantum systems, what are some of the strategies that you can use to create the isolation you might need from, you know, exterior interference for quantum computers to function properly?
Yeah, I mean, this is probably one of the main, this is a very good question. And that's basically what are these companies trying to do. That really the answer really depends on what kind of technology you're using. So, for example, if you use ions or atoms, the quantumness is already there, right? Because you have a system that has already discrete levels, and that basically already, at room temperature is ruled by quantum mechanics, and where you can encode quantum information fairly reliably. So basically, there the strategy is to make all the classical manipulations. So how you trap these atoms, how you manipulate these atoms with lasers, like to build better lasers. So it's more on the classical engineering part than on making the quantum system better, because these qubits are already very, very robust. So that's why people poured 2 billions in IonQ, for example, because that's very attractive, but they have other drawbacks. For example, they're slow. But compared to superconducting qubits, which is the other, I would say, big, contendant in this race. And superconducting qubits is basically an artificial atom. So you take a circuit and you make it as close as possible to an atom, so that has discrete levels that you can address, and you can basically build a computer out of it. And in that case, the strategy is to is more fundamental in a certain sense, because you have to really find maybe new materials that make the system more isolated, that allows this fragile superposition to last for longer times than they do now. But they have other advantage. They are already in a circuit. You don't need lasers, and they're faster than atoms. So they're both platforms are good and bad, and nobody knows who's going to be the winner at this point.
We have a question specifically about the systems that you are engineering in your lab. So you talk about using different types of atoms. Is there an advantage to choosing a particular type of atom? How do you decide what you're using for the building blocks?
Yeah, that's a good question. And yes, of course, yes, there is. So I could talk for hours of which atoms is the right one to use, etc. I would say that the short answer is you want an atom that has two levels that are very robust, so that you can encode information there, so that you have your qubit. And there are plenty of choices out there. Another requirement might be that your laser are not too crazy, like too UV and stuff like that, so that it's easier, and they're commercial, they're cleaner, and so on and so forth. So there are atoms that also fulfill these requirements. And so definitely there is a lot of even in the in the atom community, in the AMO community, as we like to call it, there is a lot of different choices. We say pick your poison. Every atom has its own drawbacks and advantages. So and even right now it's not clear, even in that case, what is the best atom. So different companies are betting on different atoms.
So stay tuned to find out the winner.
Yeah, exactly.
As far as that question is concerned. So there's a question asking about quantum qubits, and what are the requirements to implement quantum algorithms practically, and like how does that compare to the status of the systems that you're able to build now?
So, sorry, can you repeat the question?
Yeah, so how many qubits
joke
they're joking in the panelist chat. So the question was asking, like, how many qubits would you need to implement quantum algorithms practically, and how does that compare to the current status?
Yeah, so so to get something useful, so the answer is twofold. You can stack many qubits. I showed, for example, an ion chain of 77 qubits, right? That's already quantum supreme. But then you can also take a chunk of, of atomic purely material and say, this is my quantum computer. So what you need when you stack many qubits, you need to have at least, so if you have n qubits, you want at least the possibility to run n squared or even n cube quantum gates among them. Right? Otherwise, you're just, if you don't have enough operations that you can do. So the answer is twofold. You need enough qubit, and you also need enough coherence time, or, computation time to actually use all those qubits. And I would say that right now, I think Google did an experiment with 53. I also personally did an experiment of very specific. It wasn't an algorithm. It was something about many-body physics with 53 actually, that is probably, 5360 qubits are probably in the range where classical computer might actually struggle, I would say, and be like greater than, basically.
Can I tack something onto that? Which is that question is, it's very, very difficult to answer in general. So I think that what Guido was answering is for the first useful applications,
Yeah.
how big of a quantum computer would we need? But for something like factoring, the answer is totally different.
Oh, yeah.
Factoring, the answer is we need like millions of qubits, much, much better than we have now, right? So there's some applications that these smaller, maybe 60 qubit, 100 qubit type scale, we can do really interesting, useful, practically even, to company stuff. That's the hope. But for other things, like some of the famous things like database searching and factoring, you actually need 1 million qubits and to increase your quality another factor of 1,000 or more, right? So, so there's plenty we can do now, but there's also plenty of room to grow.
And I think that is a perfect note to end on, that actually tied together a bunch of questions that were in the chat asking about practical applications and where we are on the path to achieving those and seeing those. So I'd like to thank both of our participants, Dr. Pagano and Dr. Hazzard, for joining us today and sharing this really fascinating talk with us. And thank you to all of our attendees for tuning in this evening to learn more about the really interesting quantum research that's going on at Rice right now. We hope you'll stay tuned to see more about what's coming out of these labs in the future. Thank you, everyone, and have a good evening.
Thanks. See y'all.
Bye, everyone.